Good morning. Um, to address important questions in science, you should have some data. And if you look at the IMD data on monsoons, it goes back by about 100 years. That's not quite enough because you look through a window, the window is small, your scenery is also small. But if your window is bigger, you can look at a larger scenery. So this window of 100 years through which we look at the past has to be expanded. So what we do is we look at natural archives which preserve information about monsoon changes in the past. So this is my talk is about looking at the past and how do we infer monsoon changes over India over thousands of years. So the advantage is we come to see things which we don't see in the last 100-year cycle. For example, the previous speaker mentioned the desiccation happening for the last 50 years or so. Now, looking at some archives like tree rings in Nepal, Himalaya, and all the other parts of Himalaya, we see that this desiccation is not only 50 years; it goes back to about 200 years. There is a slow change which has been happening. So these are the things which one comes to know by looking at changes in the past. So I will give some overview of what we have learnt in addition to what we already know from the published literature. So it is important to, when you go back in time, for example, the best way to measure monsoon rainfall is to put a rain gauge and measure every day how much rain is collected. That is the most precise way. But if you go to thousands of years back in time, you have to rely on indirect methods. So the proper calibration is important, and we use oxygen isotopes, which is this is delta 18O. I will explain what this is. So we measure oxygen isotopes and we use this as proxy for monsoon rainfall, and I will discuss some new results on past monsoons. New results are based on tree ring chronologies. Trees have annual rings, and these annual rings we can measure the oxygen isotope and reconstruct how the past rainfall has changed, monsoon has changed. And then you have ocean sediments, you have the fossils in the ocean sediments which have recorded the oxygen isotope change in the sea, which relates to the monsoon. And then of course cave deposits like speleotherms, they are called stalactites and stalagmites, which also preserve the oxygen isotopic composition of past rainfall. And then we ask some science questions and the conclusion. This is the plan of my talk. Before we go into the talk, some definitions. Holocene refers to a geological period which is roughly last 10,000 years. So most of my talk I will concentrate on the last 10,000 years, how the monsoon has changed. Speleotherm refers to a cave deposit. It can be a stalactite or stalagmite which grows in caves. I will show some pictures later on during the talk. What is a monsoon proxy? A monsoon proxy is something that preserves the signal of monsoon. It can be either a wind proxy or a rain proxy. It can be a proxy for past monsoon rainfall or wind intensity. So these are the two things which we look at. And the oxygen isotopic ratio is defined as the abundance of oxygen 18 to oxygen 16. So oxygen has three stable isotopes. They are not radioactive isotopes, they are stable isotopes. They don't decay. Oxygen 18, for example, in the water bottle kept here, it is all H216O. Normally most of it is made of 16O, but about 0.2% of it is 18O. Small amount of oxygen 18 is there present naturally. And the amount of oxygen 18 present naturally in different things change with processes. For example, when there is evaporation from the ocean, H218O being slightly massive, it doesn't evaporate at the same rate as H216O. So the clouds, when they form from the sea, the cloud will have more of the lighter isotope H216O compared to the heavier isotope. And then the clouds come over land and then they precipitate. So the oxygen isotopic composition of sample to sample varies because of the physical-chemical processes which take place. So whenever there is a physical process like evaporation or condensation, or there is a chemical reaction, the isotopic composition changes, and these isotopic compositions can be measured using a mass spectrometer very precisely, and this can be used to reconstruct past monsoon variations. So this oxygen isotopic composition is measured as in per mil units. All of you know percent, one dot, slash and one dot, that is percent. Here if you see there is a symbol and the lowermost end of this thing, this is called per mil, this is parts per thousand. So it's percent means out of 100, per mil means out of 1000, because these numbers are small, we use per mil symbol. So let us go to when you want to look at the past, you have to go to a place where the signal is very strong. The monsoon signal is very strong in two places. For example, in the Western Arabian Sea during the monsoon, Dr. Krishnan showed a lot of wind trajectories. This is a very big jet there called Findlater jet, and that causes a lot of upwelling in the ocean. So that part, this part, which is Western Arabian Sea, this part gets a lot of upwelling during the monsoon, and the surface temperature, sea surface temperature reduces to about 4 degrees. That causes a very significant monsoon signal. So if you look at people, what they have looked at, people when you want to look at the monsoon radiation for the last several thousand years, millions of years, people have go to such places where the signal is very strong. So what is the signal they look for? Normally in the ocean, there are organisms living, they prefer certain temperatures. Some species prefer to live in warm temperatures, some species prefer to live in cold temperatures. So those species of animals or these fossils which we get, if there are cold living species, for example some polar species which are living only in cold regions, whenever such upwelling and cooling is there, they prefer to come in the tropics. So one such species is G. buloides. I will show you a picture later on. G. buloides is a foraminifera which secretes calcium carbonate. Size is about 400 microns. Small shell which is made, and that grows here abundantly. That is interpreted as the indicator of past upwelling. So when people count the number of these G. buloides, they interpret it as upwelling intensity. So higher the abundance of these particular species, higher the upwelling, therefore the monsoon is interpreted to be very strong. Whereas when you come to India, you can see on the western side, Western Ghats, Krishnan also showed a picture of modern day monsoon. He showed an average picture. If you see a blue there, if you remember his slide, there were two big blue patches in over the Indian map. One is the Western Ghats, another is Northeast. These are the places where you get very high rainfall during the monsoon season. So in Mangalore, this region gets about 400 millimeters of rain, whereas the average, all India average about 1000 millimeters. This is 4000 millimeters rainfall here. So that runs off into the sea, and the salinity reduces significantly in the coastal region. Whenever there is runoff is higher, the salinity is lower. That is the signal. Now, unlike in the Western Arabian Sea where there is no calibration, it is only a qualitative indicator, the abundance of the species. Here we have a quantitative calibration. This is the calibration which you see, x-axis salinity, y-axis the oxygen isotopic composition of the surface water. Whenever the salinity is high, that is no runoff, no monsoon, poor condition, drought means the salinity will increase. The fresh water supply is cut off, salinity will increase, the oxygen isotope also increases. Whereas when the monsoon is strong, it comes towards this direction, salinity decreases. There are in the coastal region because of runoff, salinity decreases and oxygen isotopic composition also decreases. So there is a good calibration in the Western Arabian Sea in the oxygen isotopic composition of surface water and salinity. The same thing is preserved in the sediment cores also. When you collect sediment cores, say for example when you go from south here all the way up to north and collect sediment cores, you see the precipitation is quite high in this region. As you go towards Gujarat and desert regions, the precipitation is small. So you will get low salinity here and high salinity here. This is also preserved in the fossils, oxygen isotopic composition of the fossils. So we have very strong calibration to interpret the changes during the last 10,000 years, and we see the monsoon has been increasing steadily. This is precipitation minus evaporation in millimeters. So monsoon has been steadily increasing during the last 10,000 years. This we published long time ago, 16 years ago in EPSL. But 3 years later, Gupta et al. Published a paper which said that the monsoon intensity, the wind intensity has decreased because the G. buloides abundance has decreased during the 10,000 years. So these two are the contrasting things. So the question we asked is, When we see the runoff has been increasing continuously in the Eastern Arabian Sea due to increasing monsoon, the Western Arabian Sea signal sees that the monsoon intensity has been weakening over the last 10,000 years. So this is the question to be addressed. So we address this question using various proxies. Here the same thing is shown here. This is a speleotherm record from the Arabian Peninsula. This is the Gupta records of G. bouloids abundance, and this is some plant wax from the Arabian Sea. These three records show very clearly that the monsoon has been decreasing in the last 10,000 years. Now we look at speleotherms. Speleotherms form in caves. There is a rainfall and the soil is rich in carbon dioxide because of plant respiration. The water, when dissolved in carbon dioxide dissolves in water, it becomes acidic, dissolves the calcium carbonate, which is the limestone here, and when the water slowly drips, you form calcium carbonate. And the oxygen isotopic composition of this calcium carbonate gives you the oxygen isotopic composition of the rainfall which occurred over the surface. That is the assumption. And you see a man standing here. These are speleotherms. These are the cave deposits. They are called stalagmites, and these are called stalactites. And they can go back to thousands of years, millions of years. They can be precisely dated using uranium thorium isotopes. So how do we interpret the oxygen isotopes? The oxygen isotopic composition of rainfall is negatively related to the amount of monsoon rain in a negative way. That means for every 100 millimeter increase of monthly rainfall, the isotopic composition reduces by about 1.5 per mil, whereas the experimental accuracy with which we can measure is only 0.1 per mil. So very precisely we can measure. Throughout the tropics, the International Atomic Energy Agency has measured all these places. People have measured the isotopic composition of rainfall, and it also shows a nice negative correlation. So this is the correlation which we use to convert the oxygen isotopic composition of speleotherm to the amount of rainfall. Now, it is important that the calibration proxy is properly calibrated, so we get accurate idea about how the monsoon changed in the past. One problem is that rainfall measurements are available for 100 years, mainly in metros. But if you want isotopic composition, it is not available. Isotopic composition is available in very few places over India. So what we do is we run what are known as isotope enabled general circulation model. Just like Dr. Krishnan showed you results from general circulation models, there are models which we can also, in addition to simulating the precipitation amount, they can also simulate the oxygen isotopic composition at various places. So there is a batch of models called stable water isotope intercomparison group 2 models, 10 models, and we compare these to 10 models. So this is the region which we look at, the core monsoon region defined by Goswami, which was also shown by earlier speaker. And this is how these different models, all these model names are given here, and this is how the monsoon simulated. You can see large variations in the actual, though all of them produce precipitation during the monsoon season, the amount of rainfall and the season wise variation is quite different. This can be easily seen on this right hand side. What you see is what is in a Taylor diagram. Taylor diagram has standard deviation of the model in this axis, and the correlation is plotted here. So any model is good which has low standard deviation and high correlation. Correlation is high, whereas standard deviation is low. That is a good model. So you can see some models have been nudged runs, they show very good correlation. Some models show very poor correlation. Now, if you look at the multi-model comparison of spatial pattern of rainfall, many of them are not able to really predict, because these are the CMAP and these are the actual measurements, whereas you see the standard deviation and correlation coefficients are different for the simulation of spatial pattern. And for oxygen isotopic composition also it is quite poor. So this is the interannual variations. Interannual variations, some models are able to produce very good results. So the question we are asking is, how much is the correlation between the oxygen isotopic composition of rainfall and the monthly mean as recorded by these models wherever caves are present. I am showing Mamluk cave, Akalgavi cave, Dandak and Baratang caves. These are the caves located various places which we have been studying, and in all these cave locations is there a relation between oxygen isotope and the June, July, August mean, summer mean? Yes, because this negative correlation is the red patch. You can see red patches everywhere. So there seems to be the models are able to simulate this oxygen isotopic composition. In addition, the global network for the isotopes in precipitation GNIP data, when we look at this region which gets northeast monsoon rainfall more than the southwest monsoon, they are very sensitive, and there the amount effect is very significant. So if there are caves in Sri Lanka and this part of the India, they are best suited for reconstructing monsoon rainfall. Now this is about speleotherms. This is an introduction where we look at only the calibration of the proxy. The actual results from speleotherms I will be showing toward the end of my lecture. Now tree ring chronologies have been constructed, new tree ring chronologies, and for example Sano et al. Who worked with me, we showed that the Holocene last 220 years Nepal Himalaya monsoon has declined. So this is published in one of the journals called Dendrochronologia, which is specialist journal for people studying tree rings and climate, Dendrochronologia, and we have shown based on one particular site in Nepal that in the Nepal Himalayas during the last 220 years monsoon has been steadily declining. Now what we have done is we have increased the number of sampling sites. So in all this paleoclimate, one thing one should remember, this all labor intensive. You have to go to the field, collect samples, make analysis. This takes years and years. It cannot be quickly produced. Similarly, cave deposits, you have to go to the caves, explore, bring them, date them, and only after dating them you know whether they are falling in the Holocene or they are millions of years old. Then you have to go back, and this is all done by trial and error, because in the field you don't know what is the age of the sample you are collecting. So over a period of years, 10 years of hard work, we have collected samples all over the Himalaya, 1, 2, 3, 4, 5, 6 places we have developed. We are not only looking at the ring width, we are measuring the oxygen isotopic composition, which is a more precise measurement of, gives a measurement of rainfall. Using these are the chronologies. I will skip all these details. The oxygen isotopic composition is very highly correlated with the monsoon rainfall, and this is the place. Long term correlation is quite negative. See, the oxygen isotope is negatively correlated with the amount of rainfall. This is the amount effect, and these are the correlation coefficients. I will skip all these things. I am going forward. And if you look at the stalagmite results from northern India and tree ring record, there seems to be some similarity, but there are different proxies one should remember. This is an important curve. People show that the land sea temperature contrast has been decreasing. So the blue one is the Indian Ocean SST. Indian Ocean is warming, as Krishnan pointed out earlier, and the Tibetan plateau temperature is not warming so much. So the land sea temperature contrast has been decreasing. This was also shown by Roxy et al. As mentioned by Krishnan. So the land sea temperature contrast is reducing the last 200 years. This is also Roxy et al. Paper, which they showed very clearly that the SST in the Indian Ocean has been increasing. The precipitation over central India is decreasing. This they attributed to the reduction in the land sea temperature contrast, but there are issues with this, as Krishnan has mentioned. There are other issues which has to be, it's still an open problem, but this is true as far as data is concerned. And what we have done using this training data is to show that this has been there, this declining trend is there for the last 200 years, it is there. So this is the result. This result is red curve, H5 regional tree ring. Using the Himalayan tree ring signals, whatever we say, this land sea temperature contrast is highly correlated with the tree ring oxygen isotopic chronology. So whenever the oxygen isotopic composition is increasing, that means there is a reduction in the monsoon. So this reduction is not only restricted to last 50 years, which you see very clearly, but it is a slow cycle which has been happening for the last 200 years. So what we found in Nepal Himalaya based on one particular site has been replicated over the entire Himalaya, mostly using 5-6 different sites. We have replicated this, and we now have very solid evidence that over Himalayan region also, not only in central India, in the Himalayan region also the monsoon is declining for the last 200 years. And then the ocean sediments, now more measurements are available from Deshpande et al. And other people who have looked at the oxygen isotopic composition in the ocean, and we are able to in a better represent these things. And when we look at the many ocean sediments, for example, if you go here, this curve shows you the many ocean sediments have been measured. In 2000, we published, I showed you earlier on, in 2000 we published a paper based on a core of Mangalore that the monsoon rainfall has been increasing, not decreasing, over the last 10,000 years. Now many other people have done cores all over the place, from equatorial Indian Ocean all the way up to north, so many cores. If you look at the results of all these independent workers, all of them show during the Holocene the oxygen isotopic composition has decreased. That means the rainfall has been increasing. Monsoon rainfall has significantly increased. All of them show. So the conclusion is based on both the land evidence and evidence from the Eastern Arabian Sea, the paleoclimate data very clearly show that during the Holocene, monsoon has not declined. Monsoon has only increased. Rainfall has only increased during the last 10,000 years. Now we go to speleo terms. We have analyzed many speleo terms. These are the back trajectory calculations. This is a cave called Belem cave, and this is the back trajectory analysis. So all of them get rain from this region. This is how a sample looks like. You have bands, and these bands are dated using uranium thorium, and we have now a data set for the last 10,000 years. During the 10,000 years, you see the oxygen isotopic composition has not significantly enriched. It is more or less stable. In the early stages, there was an increase in monsoon, there was small decrease, but overall trend, if you see in the last 6,000 years, there is no change. I mean, it is not going to, it is not declining. There is no declining trend as mentioned by Gupta et al. And all that. So we have now solid evidence to show that the monsoon rainfall, if at all, has increased slightly, but it has not decreased during the last 10,000 years. So what are the questions we are asking? Science question. People earlier attributed that this curve, this dotted curve which you see here, the insolation, incoming solar radiation. They say incoming solar radiation has been declining during the Holocene, and therefore the monsoon intensity has also declined. But whereas we don't see one-to-one correlation between the solar insolation and the monsoon. So this is different things. They are not related. And we have also done some proxy comparisons between different places, and there seems to be evidence for the little ice age reduction in rainfall and medieval warm period increase in rainfall are also seen in this thing. So I would like to conclude my talk. We have gained understanding on interpreting the oxygen isotopic composition, because any paleoclimate system has to have proper calibration, and one has to spend a lot of time to improve the calibration. That is what we have done using GCM models. There is a clear evidence for decline in monsoon rainfall over the Himalaya during the last 2 centuries. Eastern Arabian Sea sediments confirm that there was no strong decline in monsoon over the Holocene. The Indian summer monsoon reconstruction based on 3 stalagmite samples show rapid increase in monsoon during early Holocene, and although solar insolation plays a major role, the whatever millennial scale, centennial changes cannot be explained using these internal forcings. So these are some results which I shared with you. So I would like to thank the organizers of Indian Science Congress, especially Dr. D. Narayan Rao for inviting me for giving this talk, and I would also like to thank collaborators who helped me in building up these networks, and this program was funded by ISRO GBP. Thank you.